to mention, if you didn't already see my the note I sent yesterday about the thing to use in the format string for assignments 8 and 9, you want to use, and I'll just type it. So normally for a 64-bit int, we'd use the format string LX, okay, and that's fine in most circumstances. The problem is that, let's say that you had the number 5, then this would print it as, right, 5. Okay, great. But since we're kind of smushing together two 64-bit numbers to make a 128-bit number, if you had that, you would be omitting a bunch of the leading zeros that might actually matter. Okay, and so if you do %016LX, what you would get then would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then it would print it like that with all the leading zeros. Now, in most cases, we don't want all those leading zeros, but in a few we do, and this is one of them. So that's how you override it. When we do all this stuff with floating point here in a few weeks or whenever it is, you can also do this sort of thing where you control how many digits you can print of a floating point number. And with a floating point number, that's really handy because you can control how many before the decimal point and separately how many after the decimal point. So if you need to, for example, if you were doing a banking kind of thing where you wanted precisely 2 digits after the decimal point, right, for the cents part, then you could sort of format it that way. So anyway, so yeah, those of you guys who already turned it in, did you update that before you turned it in or no? The override, you didn't? Okay, so don't worry about it. You don't have to resubmit it, but the reason that it's important to do this is because depending on what test numbers you used in the addition, you might be getting the correct results, but just because they're being formatted incorrectly, it looks like you're getting wrong answers, even though in fact the addition was correct. So that's just the only note I wanted to make sure we were clear on. So, okay. So today I want to sort of talk about a little bit more about the stack and how we use that in terms of memory. So last time we were using this loop thing as an example that just printed the string a few times, okay? And what we said was, well, what did we notice about the flags registers and registers 0 through 18 when you call a subroutine like printf or something? What happens to them? They get nuked, right? Okay, so registers 0 through 18 are not obligated to be saved by a subroutine if it uses them. It can do whatever they want with them. Okay, registers 19 and up are obligated to be saved or preserved by a subroutine. Okay, and so what that means is that a subroutine is obligated to return those registers to their original values before it finishes. Okay, and this is why this is why in all of our programs, right, we stored, well, at minimum x29 and x30 to the stack, okay, the link register and the frame pointer, so that if we had called a subroutine in the middle of our program, then, or actually, no, sorry, like think from the operating system's perspective, like our program is a subroutine, right? And so when our program starts, the link register and the frame pointer are in a particular state, and we need to restore those to their original state at the end of the program before we return control of the operating system. Okay, so printf, like if we were to look at its source code, basically, we would see the same sort of thing, that at minimum, it would be preserving x29 and x30 in the midst of its own function, and then restoring them back to their original values at the very end of the of printf before it returned to the operating system. Okay. Now, in our case, we did not make use of any of the registers besides, well, okay, I guess technically we did after we modified it, right? But so at minimum, we need to save x29 and x30, but there might be others that we also need to save, okay? And so, the difference is, in our case, so let's put this back the way we had it originally, which was we had, let's see, we put this in register 1, 2, and 3, and then we compared register 1 to register 3, and then the addition was, let's see, it was x1 was the destination, x1 and x2 were what we added together. Okay, so this is how we had it before we did any changes, and this is what had that infinite loop, because when we came back from printf, the values in x1 and x2 were, and x3 for that matter, were all jacked up, right? Because printf is not obligated to preserve them. Okay, so let's say that we left it this way. Okay, if we ran it as is, we'd get like what happened last time, which was that infinite loop. Okay, so what can we do instead? Here and here, both before and after printf. Okay, what should we do if we're going to insist on still using registers 1, 2, and 3? Yeah, save them to memory right before printf, and then immediately after printf, pull them back off of memory. Okay, so we're going to push these things onto the stack and then pop them off of the stack. All right, so how does the stack work? So the stack is really just a segment of memory that has a special name, okay? And the stack pointer basically points to wherever the bottom of the stack is. Okay, now that may seem funny to say the bottom of the stack as opposed to the top, but so let's look at the instruction that we have up there at the very top. Okay, store pair, right? So this is a single instruction that stores 2 registers to memory at once. And you do this often enough that it's nice because you can double your throughput. Okay, which pair are we storing? X29, X30. Okay, whatever. That can be whichever registers you want. But then what's this brackety stuff mean? Okay, what this is doing is it is pre-decrementing the stack pointer. Okay, so originally the stack pointer is, here, okay, whatever it is. And what this is doing is saying subtract 16 from the stack pointer, that makes it here, and then put the stuff onto the stack. Okay, so it's decrementing before it actually puts things on the stack. Okay, now, there's a couple of things there. Why does it need to be 16? There's actually 2 reasons for that. Well, first off, if we're storing x29 and x30, how much data is that? Yeah, each one is a 64-bit register, so 8 bytes, and there's 2 of them, so that's 16 bytes. So, well, we got 16 bytes to store. We better make room for 16 bytes to store. Okay, so that's reason number 1 is just the cold hard math. But the other thing is that, and this is a hardware limitation slash design decision. I'm not sure what you would call it. The stack pointer on ARM must be a multiple of 16. Okay, so you cannot use a stack pointer that isn't a multiple of 16. If you do, you will get a bus error, a hardware error. Okay, now, how many of you guys have been cross-compiling and running this on your laptops with QEMU? Like you cross-compile something to test it and then run it in an emulator. Okay, if you do that, the stack pointer does not have to be 16 byte aligned. Okay, and so I ran into this 3 or 4 years ago where I wrote a program. I didn't have my Pi with me. I was at Starbucks or whatever. Okay, I needed to store a single register, and so I just did -8 instead of -16. Okay, that makes sense. Ran it, worked fine. Next day, gave the code to the class. They ran it on their Pis, and what happened? It didn't work. Okay, and it was that issue, right? That the stack pointer was not 16 byte aligned. Okay. Okay. So so the stack grows downwards, and so I think the example, like the way to kind of think about the stack or as a concept would be like one of those cafeteria plate holder things where it's like spring loaded and you push a plate onto the top. And you guys know what I'm talking about? No? It's like, okay, so imagine like there's a circular hole and like a big spring, okay? And you've got like 150 dinner plates, right? And you put one onto the top, you push it down, and the spring compresses just a little bit, right? And if you put another plate on and push, 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 and eventually you end up with this stack of dinner plates. And then because it's spring loaded, if you pop one off, you pull off a dinner plate, then the spring raises it so that the next plate is all right there all the way at the top, and you don't have to reach all the way in to get the next plate. Okay, so the stack sort of works like that, in the sense that we push things on top of or onto the stack, and we pop them off of the stack. Okay, now the thing that's going to be maybe slightly irritating is that the stack grows downwards. And when I say downwards, I mean in the direction of lower memory addresses. Okay, so if our stack starts at, and I'm just going to make up a number here, address 40000, okay, then if we expand the stack by 16 bytes, then it's actually going to be 3 whatever, whatever, whatever. Okay, so the stack grows downwards in the sense that it starts at something, and whenever you expand the stack, you're actually subtracting from the stack pointer. So it grows downwards in the sense of from high memory address to low memory address. That's just the way it is. Okay. And so this is why this -16 is actually a minus, because to expand the stack, you're actually subtracting from the stack pointer. And then on the other end of our program with the symmetric load pair, okay, if you're shrinking the stack back to the state that it was, well, if I expanded it by 16 bytes, I need to unexpand it by 16 bytes, okay? And yeah, now in this case then, what's the difference here? Here, the 16 byte change happens after you pull the stuff off the stack, not before, okay? So in the very first instruction, we expanded the stack by 16 bytes, and then we put the 2 pieces of data in the places that we had just created, okay? On the last instruction, we're pulling them out of memory and then shrinking the stack to cover up our tracks, Okay, so do you see how those are kind of complementary processes? Okay, the other thing about the stack pointer is that it should end at exactly the same state that it started in once your program gets to the very end of it, okay? Now, as we're gonna see, when we start doing things like subroutine calls and recursion and whatnot, your stack is gonna be changing as the program is running, okay? But for every time you expand the stack, there should be a corresponding shrinking of the stack someplace else. Okay, does that make sense? So that your stack pointer ends up in exactly the same state that it at the end of the program as it started at the beginning of the program. Now, if you mess that up and you don't get the stack pointer back to where it should have been, then what can happen is your program can try to access memory that's outside of what the operating system has allocated to it, and you'll get segmentation faults. Okay, so has anybody run into a Seg fault yet in any of these programs? Yeah, okay, that's usually what's happening, okay, is either you're trying to access memory like you're from someplace you're not permitted, okay, or, and so in C, this would happen if you were, for example, tried to put a string in memory where you had allocated for an integer, and the string was too long, and so you started wiping out other data. Okay, so that could happen. Or when you're working in assembly, what usually is the cause for this is a stack pointer problem. Okay, that the stack is not shrunk and grown in sort of symmetric fashion. Well, better late than never, Farden. I don't know. Can gentleman coin be non-integers? No? Okay. Okay, so I can't fine Farden half a gentleman coin? Okay, yeah, yeah. All right, so anyway, okay, so what we need to do then is we need to store, uh, in our cases, which registers are we using that we need to preserve? We don't need to preserve X0 because we're gonna have to load that back anyway. Okay, we already have a load instruction there, but which ones do we need to preserve in this case? 1, 2, and 3, right? Okay, which is interesting because of course that's not a pair, right? So let's store 1 and 2 to the stack. Okay, and then what else do I need to store to the stack? Well, X3, okay, how do I store a single register to the stack? It's not STP because that's store pair, it's STR, okay? But then this part is the same, okay? So even though I'm only putting 8 bytes onto the stack, I still have to grow the stack by 16 bytes. Why? That does seem wasteful, okay, but why do I have to do that? What was the reason? Yeah, the stack pointer must be a multiple of 16, okay? So does it seem like I've wasted 8 bytes worth of memory? In a sense, yes, I have, okay? But you'd have to do that, okay? Um, okay, so if I do that, then what am I going to do on the opposite side? Unload it, okay? Or, okay, so actually this is an interesting question then. Which order should I do it in? Should I do the pair first and then single register, or the other way? The single one first? Why? Why does that make sense? Which is to say the bottom of the stack, but since it grows downward, right? This is a perspective issue. Yeah, but so let me change the question, and I think you guys will see why this makes complete sense. How did I put my shoes on this morning? What did I do first to put on my shoes? Well, first, I'm wearing socks. So I put the socks on first. Then I put the shoes on. Okay? When I get home tonight, how am I going to undo this process? I do them backwards and reverse each individual step. Okay? So the opposite of putting on a sock is taking off a sock, and the opposite of putting on a shoe is taking off a shoe. But I also have to reverse the order in which I do those, right? It's not going to work very well if I try and take my sock off first. I have to take the shoe off first and then the sock. Yeah? Okay, so to invert the process, we need to invert not only each individual operation, but also the order in which we do them. Okay? We? Who know? We. Okay. Where's Owen? And Matt? And, I guess, yeah. Huh? Yeah, I bet. Okay, so we need to reverse our order here, and so we need to load x3 from the stack pointer and then grow the stack by 16, and then we need to load our pair. Oops, what was it? X1 and X2. Okay, in sort of symmetric fashion. Okay, so what this will do then is, as we saw, printf is going to mess up all of the registers 0 through 18, okay, because it's not obligated to save them. And this way, when we come out of printf, we can pull those things back off the stack, restore them to their original values, and then we're good, right? And so we should not end up with the sort of infinite loop that we ran into last time. Yeah, Drake.
Would it be LDP at 29?
Yes, thank you, load pair, because we're pulling off 2 of them. Yeah, okay. Okay, so we'll run this and double check that everything works, and then also kind of look at this in GDB. Now, there's, I guess, one other register that we could consider saving, okay? And which register is that? Now, it's not so relevant right now, but what register do we also need to worry about a lot of times? Like, particularly in assignment 9. Yeah, the one that's got all the flags in it. Okay, so the processor status register. Because as we saw, what happens to the carry, overflow, negative, and 0 flags when you go before and after printf? Those also could get changed, right? Okay, so we could preserve, we could, for example, move the processor status register into X4 and store it too, and then pop it back off the stack when we need it. Now, in this case, we can get away without doing that, and the reason is because what sets the flags, right? The flag registers, if they get changed by printf, okay, fine, but what is it that changes the value of those flags? What types of operations? Yeah, any of the flag setting arithmetic operations. Okay, so, and this is what you would be using a lot in assignments 8 and 9, right? Add C, add CS, add S, and add, right? Okay, so which of those 4 actually set flags? Add CS and add S, right? The S. Okay, so any of the flag setting arithmetic instructions, okay, are we using any of the flag setting arithmetic instructions here in this example program? No. Okay, so don't have to worry about that. What else sets flags? Well, the comparison, right? And really, what is the comparison instruction? What is that code for?
Subtraction.
It's really a subtraction, right? So CMP is really sub S. Okay, it's going to subtract one from the other, set the flags appropriately, and sort of discard the result of the subtraction. Okay, but most importantly, it sets the values of the flags based on however that subtraction ends up. Okay, so because we have to compare each time, assuming that the flag registers get nuked, we're going to come back around, and when we do that comparison, they're going to be whatever they need to be, right, based on whatever the values of x1 and x3 are. Okay, so in this case, we don't need to preserve the processor status register. We could. All right, so for sake of demonstration then, let's actually put in the instruction to preserve that register and see how that looks. Okay, we don't actually need to, but it's good for demo. Yeah, Caleb.
Can you scroll up so you can see the first few lines of the paper?
Yeah. So all we were doing is,
What would the print statement do?
oh, this?
Oh, is that all it was?
Yeah, that was it. We haven't changed it any. Okay. All right. So the processor status register. Let's deal with it. Okay. So, what is the processor status register called, or the flags that we want? What's the name of it? This is what we talked about towards the end last time. Yeah. Okay, that's the instruction to move it. But so we want to do move MRS, and let's put this in X4. What's the source of this? Okay, the four letters. Huh? NZCV. Okay. Okay, so that takes the values of the NZCV register, right, with the processor status register that has all the flags in it, and copies it over to register 4. Okay, so now that we've done that, what could I change my STR here on line 28 to be? Yeah, I can store them as a pair, right? So I could instead do store pair x3, x4, and then that, okay? Then on the opposite side, we have to kind of symmetrically do this. I need to load the pair x3, x4 off the stack. Oops. Okay, and then I need to take the flags that I popped off the stack and put them back in the flag register. What's the instruction for that? MSR, right? So it right works basically as the complementary pair to MRS. Okay, so move register to status register or move status register to regular register. Okay, good. And how many of you guys, when you see MRS, are thinking, oh, it's Mrs. X4? Yeah? No? Okay. Well, now that I've said it, you will never unsee it, right? So, yeah, okay. So I'll put the space here because what we want to think of, right, is that lines 25 through 27 and lines 31 through 33 are complementary to each other, right? We put stuff onto the stack, we're popping things off of the stack. Okay. Now, how many of you guys have already taken CS211, the data structures course? You guys probably talked about stacks a good bit there, right? And pushing and popping. Yeah, okay. That's basically what this thing is. Yeah. Okay, so any questions on the setup of this, and then we'll run it and make sure that things actually work. Yes. Yes, but the flag register gets nuked, right? So that's why we were putting it somewhere. So we might have been able to avoid having to store it to the stack, but we would have still had to move it to a preserved location. So like I could have, to Drake's point, I could have copied NCCV to like X19 and then popped it from X19 back into the register and never had to touch memory in that process because it would have only been in registers, but I still would have needed to preserve it. Well, possibly would have needed to preserve it. That's going to depend on the logical structure of your program. Okay, so to be clear, in this example, popping the flag register and storing it is completely not needed. It's not required because when we come back around to the beginning of the loop, we're going to do the comparison, and that's going to set the flags to what they need to be anyway, right? And so we didn't really need to do this. I did it superfluously just to kind of illustrate how you would do it if you needed to do it. Okay, is that okay? Yeah, it is. Excellent. Okay, all right, so any other questions before we assemble and run this thing and make sure that I haven't screwed it up? We? Gucci? All right. So, where did I put this? Conditionals, loop, okay. All right, like I said before, I'm gonna go ahead and do this with the debugging. Oops. Okay, so first off, we see, in fact, it does print 5 times, which is what we wanted, not infinitely many and not once, like we found when we were, before we preserved X0 and stuff like that, okay? All right, so that's good, but let's look at this in GDB and kind of see what's going on with the stack pointer and the stack as the program runs. Okay, so okay, so if I start now, oops, before I've actually executed anything, what is my stack pointer? It's here. Okay, so what is that? 7FFFFF, okay, and there's a convention on why it's 7F and stuff at the beginning. Okay, but for our purposes, basically, let's think of it as 050, okay, with a bunch of stuff in the front of it, okay? So that's the value of the stack pointer before anything has happened. Now, what's the instruction I'm about to execute here? This guy, okay, what's that going to do? Move the stack pointer down and then put 2 things on the stack. Okay, so make room for 2 pieces of data, shove them onto the stack, and we're good. So after this instruction is executed, what should be the value of the stack pointer? If right now it's 050, what should it be after that instruction? How about 040? Why is it 040? Yeah, because this is all in hex, right? Right, what's 16 in hex? 10. Yeah? It's kind of like, have you guys ever seen those t-shirts? There are 2 types of, or there are 10 types of people in this world, those who understand binary and those who don't. Huh? Well, you've never seen that T-shirt? Okay. Well, there used to be a company. They got bought out by GameStop, which meant that they died a horrible death immediately afterwards because, well, GameStop. Um, and this is, of course, before the whole short squeeze GameStop stock thing happened this spring. But some people made a lot of money off of. Anyway, there's a company called ThinkGeek, and they sold nerdy T-shirts and stuff, and lots of other kind of things, for like people like me. It was an awesome place to spend money. The problem was that most of their nerdy customers also were, college students who didn't have a whole lot of money laying around. So anyway, um, but that was one of the T-shirts that they had, and it was sort of like, haha, we can all get a good laugh out of this, except for our friends who don't understand binary, right? So, okay. Right, so the stack after this instruction should be 040. So let's step it, and if we look at it now, sure enough, 16 has been subtracted from the stack pointer because we just allocated 16 bytes on the stack. Okay, now, let's look at the stack. Okay, so this instruction that I put in GDB, x/something, okay, I basically am saying to GDB, hey, show me what's in memory, okay? And the 16 and XW basically says how much memory do I want to see. But the SP part says basically where do I want you to start showing me memory, what memory address. Okay, and in our case, I almost always do this starting at the stack pointer because most of the memory that we'll deal with in the course of debugging and running our programs is everything's going to be relative to the stack pointer. Okay, so what do we have that memory addresses 050 and on? Okay, a bunch of stuff. Okay, that's nothing particularly special. Most of it just happens to be zeros. Okay, but when we pushed two pieces of data onto the stack, okay, the contents of x29 and x30, there they are on the row that says 040. Okay, so what is x29? X29 was the frame pointer, which is basically the original value of the stack pointer until you start changing it. We'll talk about the frame stuff later, okay? So what is X29 before we did anything? Blah, 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 050, okay? What about X30? 4008F4, okay? Those both got put onto the stack, all right? So now how do we read this? Let's just remind ourselves. This display is showing it to you in 32-bit chunks. Okay, so what are the lower 32 bits of X29's contents? So when I say the lower 32 bits, where do you start reading? From the right, okay? So the least significant bits are down at this end, and the most significant bits are over at that end, okay? So the least significant 32 bits are there, okay? And those are stored in memory addresses 040, 1, 2, and 3, right? 4 bytes, 32 bits, okay? All right, well, what about the next highest 32 bits? It's a bunch of zeros and then a 7F, okay? And there they are, right there, at memory addresses what? 4, 5, 6, and 7. Yeah? Make sense? Okay, so what about our next value? which was x30, right? What was its value in the register right before we stored it? It was that, okay, 4008F4, and there it is. And then, of course, this stuff over there is just all the leading zeros that are in front of it, right? Because remember, X30 and X29, really all of these registers, how big are they? Yeah, they're all 64-bit. Okay, this right here is way smaller. Like, we don't need all 64 bits to represent it, but they really are there. Okay, so remember at the very beginning when I talked about the overriding, the GDB, like right here, did not override the number of zeros. So if we had overrid the number of zeros when printing, like if we went in modified GDB source code, right, what would we expect to see here? A crap ton of zeros. Okay, it's suppressing any leading zeros, except in the memory part, just to make it more readable, really. Okay, good. All right, now let's actually get into the meat of the program. Okay, because we're loading some immediates, we're doing a comparison. Okay, so we just did a comparison, right, which is really a subtraction, and what got set here on our flags? Yeah, the in flag is set, and the other four are, or other three are unset. Okay, fine. And we just did the comparison, and now we're going to look at the branch instruction. Should we branch here? No. Okay, and so we're going to load our string, and let me execute those guys. Okay, so we just did this instruction, and we just did that instruction. So what do you expect that the stack pointer is going to be now? What was it before I did any of that? It was blah, 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 040. What should the stack pointer be now? 020, because I've expanded it by 16 bytes twice. Okay, and what should we see on the stack if we look at memory? We should see the contents of registers 1, 2, 3, and 4. 1, 2, and 3 had our counter, the number 1, and our termination value, which was 5, just for the sake of example. And what did we stick in register 4? Yeah, the copy of the flags register. Okay, so if we look at the memory now at the stack pointer, well, first off, look at the stack pointer. Is that in fact blah, 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 020? Yes, that makes sense. Okay, and we haven't gone into printf yet, so nothing's gotten nuked out of all of our registers. Okay, but let's now look at memory and see, did everything get stored the way we think it should? Okay, so there's our stack, right? And because I started this thing with the stack pointer, that's why it's going to show us starting down there at 020. Okay, so look at what's at the row 020 and 030 and explain why that makes sense. Well, what's in, well, let's start with 030 because that's what we put on the stack first. What did we do first? Registers X1 and X2, correct? Yeah. All right, what was in registers X1 and X2? Was 0 for X1, that was our counter, because we hadn't yet added anything to our counter. And what was in X2? The constant number 1, okay? Does that jive with what we see there in memory? Okay, What's in x0? What did we say it was? 0, okay. And that got stored in the first 32 bits, or sorry, 64 bits. And well, that looks like a whole bunch of zeros to me. Okay, so that one checks out. What about the next two? What was in x1? Or sorry, excuse me, x2? The number 1, does that jive with what we see in memory? Yeah, okay, because that 1 there is in the least significant position, and then the rest of it's all zeros. Okay, so does that make sense? Okay, now, what about x3 and x4? What was in x3? The number 5, which was in our case just how many times we wanted to loop. Okay, and did that get stored here? Yeah, looks good. Okay, what about x4? What was in x4? The copy of the flags register, and that got stored in here, and this is where we'll have to think a little bit, as it looks like 8 with a bunch of zeros, with a bunch of zeros in front of it. Okay, so let me write this on the board all in order. So it'd be 1, 2, 3, 4, 5, 6, 7, 8 zeros, then an 8, and then 7 zeros. Okay, so this is the contents of x4. Okay, well, let's decode this. That 8, right, because really all of these things in hex are representing 4, right? Each nibble, each hex character is 4 bits worth of stuff. Yes? Okay, so that 8 means that if we were to write all this in binary, we would have a 1. Which bit is that far left one? It's bit number, huh? The very, very, very far left one. They start at 28. Yeah, it's 31, okay? So the flags register, right, uses really only 4 bits out of 64, okay? And it's bits 28, 29, 30, and 31, okay? And what was the order for that? So let's see, 30, 29, and 28. What was the flag register called? NZCV. What was it? NZCV. Right? Does that jive? Yeah. Yeah, I think I wrote it in the other order incorrectly. Yeah. Well, okay. I mean, let's just see, right? Yeah, go ahead.
So just make sure it's at 31, not 32, because it's
Exactly, right. So it just depends on how do you want to count. Is this the 0th bit or the first bit? The reason I've started counting at the 0th bit here is because that's how it is in the ARM documentation, and this way I'm consistent with the documentation, right? It's bits 0 through 31, and then the second half would be 32 up through 63. Okay, yeah. So okay, that's just a counting problem, right? But and Cade, this is how I know that the order I wrote this in on Tuesday was wrong, because which flag is set? The N flag, and that means that there should be a 1 wherever the N flag is and a 0 everywhere else. Well, because, oh God, I'm wrong again. What is 8? I'm sorry, guys. What is 8? No 1s, no 2s, no 4s. Oh, no, wait, I am right. Yeah, okay, never mind. Okay, yeah. So an 8 is I mean, we can see, right? The value is an 8. It's right in front of us, okay? And in binary, that would mean 1 followed by 3 zeros, which means that the order is this, not the way I wrote it on Tuesday, where I had it backwards. Okay. Okay, does that make sense? I mean, other than the order issue that I screwed up on Tuesday? Yeah. Okay, so the in flag is in the position that we expect it to be, and all the other flags, in this case the 0, the carry, and the overflow bits, are all 0, and that makes sense, right? We? Okay. So we just stored stuff to the stack. I'll talk about alliteration there. Okay, what's the instruction I'm about to execute, but I have not actually done yet? The printing, right? We're ready to print. Yeah, so the way this does is it displays the instruction that it's about to execute but hasn't yet executed. Okay, so if I step this, what should we see? It just printed the string, and now what's about to happen? We're going to start loading our values back off of the stack, okay? And if we look at the registers, now that we've printed, look at X0, X1, X2, and X3, right? Well, look at like X2 in particular. That is most certainly not the number 1, okay? And X3 hither, before we did any of this was 5, and now it's 0. Well, okay, why is that the case? What's true about registers X0 all the way up through X18? Yep. Printf is not obligated to restore them to their previous values. It's up to us to do so if we need them, okay? And then the other ones actually would actually be the same. So, okay, good. So that makes sense. And then look at the flags now. Printf did its thing and stored what as its flags? It had the carry and the 0 flag set. Okay, whatever. But if we did this, okay, and we look at our registers, now 2 things have happened. Okay, look at the flags register. What's it got in there? Just the in flag set, right? And that makes sense because that's what it was before we printed. So we've restored it back to its old value. Okay. What about the stack pointer? What is it now? It's back up to 040. And why is that the case? Well, we just popped things off of the stack, right? Okay, so in this case, we're going to be pushing things onto the stack, popping them back off, pushing them and popping them back off. Once of each, a push pop for each instance of the loop that we go through. Okay, just because of the way I structured it. Okay, so does that kind of make sense? We? No. Okay. And, well, yeah. But in particular, the benefit is if we look at our registers now, these 3, right, have been restored to their previous values. 0 was our counter, 1 was the number we added every time, and 5 was our top number for the number of iterations. Okay, and then X0 is still 12, or 12 hex rather, but that's okay because what do I do before printing? I'm going to load the address of that string anyway, so I don't have to preserve it because it's going to get fixed later. Okay, so questions, preguntas, and/or fragens. 9? No? All right, excellent. So that made sense. All right, so let's go back up here. And what this starts to get us towards, particularly with the storing of x29 and x30 and any other registers we might need, okay, is how do we write functions and pass parameters to them, okay? So let me do a new example here, and let me just copy this stuff. Okay, so what I'm going to do is I'm going to write a really silly function that all it's going to do is take a number in and square it. Okay, and then the outer function is going to, the main function is just going to print that. Okay, so the value, so I'm going to change my string to the value of dang it, if I could get the correct. Okay, so I'm just going to print, oops, and then let me save it someplace. Let's call this. Okay, so all right, so our main routine, the very first thing as usual, store pair, load pair. Okay, and put an exit status code for Linux. Right. All right, so that's all usual. And then what I want to do is, okay, so the way I'm thinking of this is if I were to write this sort of thing in C, okay, what would I do in C? I would do something like int, or long int, square long int n. Okay, if I wrote a function to square a number in C, it would look like that, right? Take the number in, okay, which I called the letter in, whatever, and return the value in times n, okay? I mean, it's a stupid function. You would never actually write this for real, but it makes for good demonstration. But that's what the syntax would be, right? And what data comes in? A long int, or whatever else you want. And what data goes out? Also a long int. Okay, now, in C, right, you have to be careful and specify what type of data is going in or out, okay? And what are the things that can come in or out? Integers, long integers, floats and doubles, okay? And then if it's not any of those, okay, maybe a character, which is a single byte, and possibly stuff involving pointers, right, as inputs or return values. Okay, great. Where do these things have to go, though, right? So if I wrote this program in C, and up in my main routine, I said something like, you know, number equals square of 5, okay, where would 5 be in registers, and where would the answer 25 come out in the registers? Okay, so if we wrote this in C and then assembled it there and debugged it and stuff and read through it, where would those things be? What's the convention? Yeah, okay. So if in my main routine, okay, so somewhere up here, I'm going to write some code that is going to do something like this. Okay, so it's going to pass the number 5 to my squaring function. The function's going to do whatever, and it's going to return 25 back. Okay, great. In terms of the registers, where will the number 5 and the answer 25 end up? Right, that's the question. Where do we put, how do we pass parameters to functions? Where must they go? They got to be in registers somewhere, right? So which ones? Yes. Yes, x0 through x7 in order, okay? Now, in this case, how many parameters am I passing to my squaring function? Just one, okay? So the number 5, I need to put where? X0, because that's the very first one, okay? And then the function should return them in x0 through x7 in the same order, okay? So in this case, the function returns only one value, right? It really can only return one value. It's going to return 25, but where is it going to put the number 25? In x0. Okay, so let's say that we were writing a function that took in 4 values and did something with them and returned a single value out. Where would those 4 values need to go? They would need to go in x or w, right? 0, 1, 2, and 3 in the corresponding order. Okay, does that make sense? Okay, now, why is that the rule? Well, it's a conventional rule, right? There's nothing about the ARM architecture that specifies this is how you have to do it, but it is the convention within Linux and for parameter passing, okay? What this means is, like, for us, since we're writing our own function, we know what registers we're putting things into. We could really do whatever we wanted, okay? But by adhering to the convention, this will make sense, because what happens if we use some other dude's function? Okay, so for a good example, right, in assignment, which was it 4, the triangle one, right, you guys had to use a couple of the math functions that C defined. What were they? Yeah, the squaring and the square root functions, right? Okay, so did we write code for how the square root function did its thing? No. Okay, some other dude wrote that, and we were just calling his function. Well, all the functions are going to expect that the input are in the registers in the correct order, and they're going to expect to return the answer in register 0, okay, assuming it's a numerical answer, and so you better be prepared to use it accordingly, okay? So, right, x0 through x7 are for parameter passing. Okay, and this makes sense because when we did printf, like if I, let's scroll back up to my format string. Here, right, if I'm going to call printf to print this string and 2 numbers, what has to go in which registers in order for that to be, to work? What's got to go in x0 for printf? No, that would go in x1. For the square function, it'll go in x0, but for the print function, yeah. Yeah, the address of the format string. x1 would be the first number, the first long integer printed, and x2 would be the second long integer printed, and we just continue down the line as many as we need. Okay, if we need more than 8, then we start to have to use in the stack, and you're having a bad day. Okay, but which could theoretically happen. Okay, so x0 gets the address of the format string, and x1 and 2 get the numbers 5 and 25, the answers. Okay, so for our function, where does the number 5 need to be? In x, well, this is kind of a trick question because it kind of needs to be in 2 places, right? Okay, so let's do the squaring. Okay, and then let's square it. Okay, so after we do the squaring, what is sitting in register x0? Well, right now nothing because we haven't written the square function. Okay, so what should the square function do? How do we square something in? Yeah, how do we do multiplication? We've only done addition up till now. Well, if add does addition, what do you think does multiplication? How about mul? Right? Okay, so what's that going to do? X0 times X0, putting the answer in X0. Okay, and then I need to return back to here. Okay, so when I come out of the squaring function, what's in X0 then? 25, not 5. Okay, but where do I want that 25 to actually be? I need it to be in X2 because 5 will go in there. Right, so that was the number I put in. And here I'm going to move X0 to X2. And then I'm going to load register X0 with the address of the format string. What did I call the string? str1. And then I can branch to printf. Okay, so why did I have to rearrange what was in which register? Well, because printf as a function is going to expect what? It's going to expect the address of the format string in X0. It's going to expect the number 5 in X1, and it's going to expect the number 25 in X2. And so I better get them all in that order. Okay. However, the convention on parameter passing is where is the inputs? They go in X0 and on, and where are the outputs coming out of? X0 or W0, whichever 0. Okay. And so I have to rearrange the registers to take that into account. Okay, does that make sense? All right, so first off, let's assemble and run this and make sure I didn't screw it up, and then we'll go through GDB, and then we'll quit. All right, so what did I call this? Assembly functions. Okay, that worked. Okay, but now let's step through it in GDB. Oops. Okay, so I'm about to call the squaring function. What's in register 0 right now? 5. Okay, makes sense. I just moved that there. Okay. And while I'm at it, what is the value of my link register? Right? 8D4. Okay, I just jumped down to the function, okay, which was later in the code. Okay, that's going to do this multiplication. Okay, whatever. But then when it hits this return, how does it know where to get returned back to? Look at my link register. Sorry, that's a program counter here. This is the line immediately after BL square. That's what it's pointing to. Okay, so that if I step, I go back up to where I came from. Okay, and so now, before I set everything up for printf, notice what's in the register X0 coming out of that thing. 25. Okay, that makes sense. Okay, and then I need to step, 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 and I'm about to printf. And what's in X0? Okay, that number, who cares what the number is, but what does it represent? Yeah, the address of the format string. What's in the number or register 1? 5. And what's in the register 2? And we're about to branch to printf. It's going to print it, and yay, we're good. Okay, so I'll just continue, and there it goes. It prints 5 squared is 25, and we're happy. Okay, does that kind of make sense? All right, so this function stuff, right? We can start to write functions the same way that we would have in C, okay? And has anybody looked at assignment 0A? Yeah, what's assignment 0A? Yeah, the Fibonacci's, but how are you doing it in assignment 0A? Well, okay, you hard code which one you want to end up with, but yeah, how could we produce the Fibonacci's? When we did this in C, how did you do it? 2 ways. Iteratively and, okay, so if assignment 0A is to do it iteratively, what do you think assignment 0B is going to be? No.
Upper to lower.
Recursion. Yeah, recursion. Because that's our favorite thing in the world, right? Yeah? All right. All right, have a good, excellent rest of your Thursday. I will see your bright and smiling faces on Tuesday next week. And goodbye, Twitch.